Welcome back everyone. And we were talking about Vertex specifier, and what I will do is just to tell you how to construct a Vertex specifier for some concrete problem called min-max path. Okay, and we will see later how Vertex specifier in the black box manner can give you dynamic algorithm. Okay, and what we have seen is like definition of min-max path, which is just a path with minimum max weight. Here, the min-max path from S to T is 7. And the important thing that we just need to remember is that if you want to specify the graph, you can specify the graph into a tree. And this minimum spanning tree preserves every min-max path between every pair of nodes. Okay. So now let's try to construct vertex specifier for min-max path problem. Okay. So the problem precisely is this, right? You have a graph and you have a terminal set S. You want to construct a graph H of size linear in S. And at the same time, for every pair UV, every terminal pair, min-max of UV in H and in G. This is preserved exactly. Okay. And I will just write H equivalent to G with respect to S. Okay. Just for warming up, suppose that your terminal set is just, you have two nodes, U and V. How should we construct the graph H? Anyone? Just an edge. So you just construct one edge, UV, and how should it be the weight? Just be the min-max of this, like U and V. Okay, good. Okay. Now let's see in the general case how it should be. Well, the algorithm will be like this. Okay, let's start with computing a minimum spanning tree of a graph. And it's safe to do that. And we can just focus on this tree because it preserves our min-max path of the graph. Compute it. And let's say that this purple thing is a terminal set. Okay. So let's focus on this tree. Next thing I will do, which is quite convenient, is to compute the LCA closure of the terminal set in the tree. So, and call it S prime. So what do I mean by this? It's just that the LCA closure is like for everything in U and V in S prime, the LCA of U and V is in S prime as well. So I want this thing and that S prime contain S. And in picture, it would be like this. So just look at the LCA of every purple thing, add it, and look at the LCA and add it. Here is the LCA here, add it, and so on. Okay. It's easy to see that you will add like the size of S prime will be just twice as much as S. So compute S prime. And then once you get S prime, you can we can kind of define adjacent pair of two nodes in S prime. Like these two guys are adjacent because there is nothing else in S prime between the path. Between the A and C, there is no terminals S prime. So just look at the adjacent pair UV in S prime. And then what we do is like similar to the warm-up case, add one edge between A and C here, right? What should be the weight of this guy? Well, just put the min-max weight, the maximum weight between in the path from A to B in the tree. So in this case, 1, 8, 6, you put 8 here. Just do this for every adjacent pair. You get some tree such that the vertices of H is exactly S prime. So this tree is of size order of S. And it's going to be correct. Like this is the correct specifier, because first of all, the tree preserve the spanning tree preserve our min max path. And why like it's enough to just do this case, kind of just apply the idea from the warm-up case. Time to construct this. This is just to compute MST, which is basically linear time. The size is also linear in S. Okay, so that's like a simple example how you construct vertex specifier, compress it into the size of the terminal set. Okay. Next thing I want to talk about is just one property of called composability. So this similarity relation, like I will say it's composable if, like, when I say that G is similar, H approximate G with respect to S, and if you have an H UV whose endpoint, both of them are in the terminal set S. If you have these two things and the following is true, then we say that the relation is composable. That is, if these two things you have, then H plus an H and G plus an H still approximate each other with respect to S. And you can observe that the relation that you preserve min-max path is composable. That is, I want to show that if G, if H is equivalent to G with respect to the terminal set, then H plus an H is equivalent to G plus an H, such when an H has endpoint inside the terminal. Right? Okay, so why is that? It's just kind of amount to checking definition. Well, if you look at for any pair ST, okay, the min max in the graph G plus E from S to T, you like what can it be? Well, you have a graph in S and T, and then you add some H. You add some HE here. After adding an H, the min-max path might not change. So it could be like min-max of the old graph. Or the min-max path might be the one where you go from S to U. Let's say this is U, and then go from B to T. Otherwise, it might be another one, which is go from S to V first, and from U to T. So these three cases, that's how you get like just minimize over all three cases here. That's the min-max from S to T in the graph G plus E. Well, the same thing is true for H plus E. You have three cases. But once you just compare this thing, like every min-max of H is the same as min-max of G. This min-max of H is the same as min-max of G. So everything here is the same. So you get that min-max of from S to T are the same in H plus E and G plus E. So that's why you get that H plus E is equivalent to G plus E with respect to S. So it's composable. Okay, so many natural similarity, like approximation relation is composable. Like distance is composable as well. But yeah, for today, we look at min-max equivalence. Okay, good. So we get some basics about vertex specifier now. So let's see how, like, given an algorithm for computing vertex specifier, how can you get dynamic algorithm? And this is used in like many papers, like a lot of them like by Gramos. The earliest one that I see is like by Epstein. And it's used also quite a lot in like the modern Maxflow algorithms, the linear time, almost linear time one as well. So my plan is to show you this reduction. Given a fast algorithm for computing specifier, you get dynamic algorithm. But I will show the one that gives you the offline one. Okay. And then discuss a bit how to make it, like how the same idea also apply and give you non-offline one, the standard dynamic algorithm. And like point you out about a bunch of open problem in this area. But anyway, like let me tell you first what are offline algorithms exactly. Okay. So what we will look at is offline dynamic algorithm. And just for simplicity, like for like convenience for notation, what I will assume right now is like for every update, for each step, instead of giving an update or a query, I'm given two things at the same time. I'm given one update, which can be deletion or insertion, as well as I'm given some query SITI. I want to know like what's the min max between S and T, SI and TI. Okay. So now the offline fully dynamic min max path problem is like this. Okay. The input is a whole sequence of update and queries. The length of this input is of size M. So when you see this M, it means that at any time, the size of your graph at time I have at most M edges trivially, just because the size of total insertion can be at most M. Okay. And this is what the point why we call this offline is because you are really given the whole input sequence, whole like update sequence. This whole update sequence is given to you in one go, and you can read the whole update sequence. It's not revealed to you one by one like before, like a standard setting. Okay. And what we want to output is to output for all I, compute min max from Si to Ti in the graph Gi. So I hope this is clear, like what is offline setting. Sometimes it's useful actually to get offline algorithm. Like it can be interesting by itself, but it's weaker than standard one. And again, trivially, you can do this in M square time. There are M steps. Each step you can compute min max. You can answer the min max query in linear time. So you can do it in M square time trivially to answer every queries. But I will show you how to get this from M to the 1.5 and then M time at the end. So you can think of this as like basically almost constant per update query. The total time is M. So on average, it's almost constant. Okay, so the high level idea that we will proceed, like that we try to do is this. Imagine that this is a timeline. Okay. What I will do first to answer the query is actually, I want to compute for every step I want to compute a specifier hi that preserves information about the graph at time I, gi. It preserves information about si and ti, about the thing that we want to query. Okay. And note that the size of hi will have constant size because the terminal set here is just 2 nodes. Okay. So given like there are like a graph in the timeline, you compute kind of smaller graph that are equivalent for each of the time. Yeah. And if you are given this hi here, then you can just compute min-max of si and ti in gi just by computing this thing in hi. Each I you can compute this in constant time. So the total time to return all these things for all I is just linear. So from the h, if you have computed hi, you can compute all these things for all I in linear time. So this is indeed enough for you to do. But what's the way how to compute the specifier? Well, the trivial way to compute specifier is just like to spend linear time to compute hi for each specifier. That takes m squared time, which is not good. And the high-level idea, less trivial way to do this is to do some like hierarchical decomposition of the timeline. What will happen, and I will go into details. This is just like a schematic thing. We just decompose the timeline into parts, into interval of length root m. There are root m interval. And for each of this interval, we will do something in linear time. And then for each of the interval here, we will get like the hi within the interval. But the time to compute each of this hi here will be just root m instead of linear. So there will be 2 levels of things. For each level, you spend n to the 1.5 time. That's high level idea.
Will you explicitly specify what are the?
I will make this into like a very details here. Yeah. Okay. Let's see the details now. Okay. To do this, I need some notation. Okay. So we divide the update sequence of length m, right, into root m intervals. Okay. There are intervals here. And let's fix one interval I. Let's say this one interval. Now, this is just some interval of the timeline. Now, for each edge in the graph, one edge will be inserted and deleted. So that like there is like an interval time lifetime of each edge, right? So for each edge E, there will be like interval of E is just the insert time of E until delete time of E. Each edge is like one interval. And once you define the interval of an edge, I can define a permanent edge with respect to an interval I, the red interval here. This is just an edge such that it stays for the whole interval. So the interval of I contains this I2. The interval of an edge contains I2. So this kind of edge that stays permanently within this red interval is a permanent one. Another one is the not permanent one or the updated one. This is just an edge such that it has some overlap with this interval, but it is like it's not permanent. So the intersection of I and the interval of an edge is not it's like it overlap. It's not empty, but it's not, this intersection is not the whole thing. Okay. And the way you should think about this to set the permanent edge, the size of the permanent edge could be as big as m. In the worst case, can be linear. But what's the size of the updated one? It's at most root m, right? Because the length of I2 here itself is of size root m. So it can have only like a root m many updated edges.
For permanent edges, should the subset sign be the other way?
You're right, thanks. Yeah. This thing should be, thanks a lot, Kent. Yeah. Okay. So these two are fine, right? Yeah, we need some notation, but yeah. Now, when you look at this interval I2 here, and given this notation, I will define the terminal set for I2 for this red interval. Before reading this, you should think of the interval, the terminal set for I. Think of it as like endpoint of edges that are updated or endpoint of the query. So everything that kind of the endpoint that are related to the interval, okay, whether it's updated or query. So, which means that it's an endpoint of the updated edges during the interval I, and also the endpoint of all the queries, all SITI within the interval I. This terminal set is of size root m too, because there are like root m updated queries in the interval I. So you can think like you have a graph, and if you look at some interval I2, there can be some updated edge within I2, some query, and yeah, the terminals for I2 is just all this endpoint. Okay. So now we are ready to describe the algorithm. What we're gonna do is this. The algorithm gonna loop through all the interval here. The interval here. Let's look at one interval. Let's say I. What I'm gonna do first is to compute a graph h sub I, h of the interval I. This graph will be equivalent to the permanent edge for the interval I with respect to the terminal set. Okay. So you have this graph. Okay. You look at this terminal set here and forget about the green thing because these are not permanent. And you compute the specifier hi that preserve information about permanent edge for interval I. And hi would have size root m. Why? Because your terminal set is of size root m. So this is where compression is going on. Like the permanent edges can have linear size, but you compress it to root m size. So this is just a graph for one terminal. Like graph hi is for this whole terminal for interval. Okay. Now for each step, small I, let's say like you look at step I. I'm gonna create one graph hi prime. Okay. How does it look like? So it's a graph where I just kind of start with HI. Okay. It's a graph where I look at an edge that is updated within, okay. I look at an edge in GI that is not permanent and add it to HI. Okay. So what is an edge in HI? It's just all edges that intersect with this vertical line, right? These are not in, what are the edges in GI? All edges that intersect with this vertical line. These two are not in GI. Okay. These two I don't care. So I look at this one that are not permanent. So it's only these two guys. And I add these two guys into HI and get HI prime. So in picture, it's like you look at these edges, they are updated within this big interval. The green one are updated in the green interval, but not everything is in GI. So let's say only two guys here is in GI. That's the guys that I add into HI and get HI prime. And now so HI prime is just kind of a graph where I kind of add an edge that is specific to GI to HI. And once I have this graph is still of size, like of size root m. The last step I'm gonna do is I'm gonna build HI, the one that I want. It's just gonna be the specifier of HI prime with respect to SI and TI. So I would get, from this, I compress it further to a graph that have size constant.
Yes. So HI was a tree, but Hi prime is not.
HI is a
Big I.
tree. Big I, yes, yeah. This one is a tree. Once you add some edges, it's not a tree. It's not a tree. Good. Yeah. Right. You should think of this as a tree, and you add some edges, so it's not a tree anymore. So HI prime is not a tree, and then you compress it to just one edge. Okay. So a lot of notation, but once we see the correctness proof, I hope like you are convinced that like this makes sense. So first thing, like my goal is to show that, okay, HI would be equivalent to GI with respect to the endpoint. If this is true, then we are done, right? This is what we want to compute for every I. There are two steps. The first step is I'm gonna show first that at least HI prime preserve GI. Okay. So HI prime preserve GI. HI prime is not like as small as HI yet, but it's preserved GI. So why is that? Well, because first of all, we have that the graph H big I is equivalent to the permanent one. But by composability, right? If you add some set of edges to both sides of this thing, this and this, they must still be equivalent. But now from the definition, HI prime is this thing. hi prime is just this thing. So this is just hi prime. And what is this thing? This is just gi, exactly. So it's this set union with gi minus this set. So it's just gi. So hi prime is equivalent to gi with respect to S big I. Okay, so we have at least we have halfway that this guy is equivalent to gi. Okay, but what we want is like we want hi to be equivalent to gi. But why is that? Well, I want to show this thing. If we have this, we are done. Well, we have that hi and hi prime is equivalent to each other with respect to s1 and t1, si and ti. This is just from the definition here, from how we build it. But hi prime is equivalent to gi, right? So because this thing is equivalent to each other with respect to the bigger set si. So it would be equivalent with respect to this just 2 points here too. So this equivalent to this thing equivalent to this, so they are equivalent to each other. Like hi and gi are equivalent to each other. Okay. So that finished the proof. Question about this? Yep.
Wait, sorry. Why did each interval take order m instead of order square root m? Maybe can you go back a few slides to where you?
I will analyze the time right now.
Oh, okay.
Yeah.
You can do just brute force in after you reduce the permanent edges, no? Essentially.
Yeah, basically after.
I'm not. I mean, be the naive algorithm with because there are only square root m edges. And you can.
Like this is basically brute force within the interval. Yeah.
Yeah.
This thing here is like brute force within the interval. We have some like a base graph that equivalent to the permanent one, and you just for each of the time inside the interval, you just add what you need to add for each of the specific I, and you just compute. Yeah, you could have just computed inside this thing.
Yeah. Yes.
But you like I want to do this just because it will be clear that from this you can
Compose.
You can compose and make it more than 2 levels. Yeah. Good question. Yeah.
Sorry.
Yes.
So this works for any composable relation, right?
This works for any composable relation.
And the second question is within the interval, why can't you recurse instead of doing this brute force thing?
You could brute force. What I'm describing here is to actually kind of recurse. Like I'm just kind of unfold the recursion into 2 for loop. Yeah. So I can just describe it as a recursion. I just unfold the recursion into 2 for loop. Okay. So let's analyze the time, right? Well, there are root m many loops here. This step takes linear time. So this total time is like m root m. About this one, the total loop that you go through this is m, but each of the step here takes root m time. So the total time is m to the 1.5.
Quick question. To build in the last step, do you compute the MS3 for comparison?
Yeah, you can. Yeah, you compute an MS3 and just compress it to one edge. Yeah. Okay, so this is a schematic thing that kind of I explain the details. You get like these 2 level things in m to the 1.5 time. But okay, 2 level of specifier give you this running time. If you have k levels instead, you would just, like divide this thing further into intervals and apply the same idea and adjust the parameter. Instead of root m, you make it balanced. If you have k level of specifier, you will get like the total time of m to the 1 plus 1 over k. And okay, note that when you compute, like if the specifier is not exact, if it has approximation alpha, when you compute specifier of a specifier, this approximation would accumulate to alpha to the k, where k is the level of things. Okay, but you would get alpha to the k approximation offline dynamic algorithms. But in our case, alpha is 1. We have an exact specifier, so there's nothing to worry about. You could just set k to be log n, and that's how you get near linear time. So what you just seen is that it's a black box transformation, right? It works as long as you if you have a vertex specifier, a fast algorithm to compute vertex specifier, and the relation is composable, immediately you would get offline fully dynamic algorithm from this. How to not get just offline one? We can do it, and it's gonna be super similar, and but it just add some more notation and makes the presentation more complicated. But the idea is just similar. So let me just claim what is true, and you can try to do it as an exercise to convince yourself that it works. That is, if your vertex specifier algorithm could handle this thing that I call the add terminal operation. What is it's like an operation where okay, you compute vertex specifier with respect to some set S, and let's say you have one more node you want to put into terminal. Let's call it V. You want to add V into your terminal set. If you can do this thing and you add V into your terminal set and you can update your specifier quickly, let's say polylog time, that's what it means by you support add terminal operation. And if you can do this, you immediately would get incremental algorithm. Online one, not offline. And by the way, many non-specifier in the literature, including, let's say, the one that preserved distance by Torab-Zwick, that one naturally support add terminal operation. Other ones something else called regulatory that preserve MaxFlow, that also naturally support this. So it's you get this for free most of the time, and you get incremental algorithm. If instead your vertex specifier can handle both add terminal operation and delete operation, I will not go into details, but you could expect that if you can handle both add terminal and deletion, you would get fully dynamic algorithm. The black box way too.
So how fast do you want those operations? Proportional to S or poly?
It should not be proportional to S. It should be independent of S. It's if you add one terminal, you should spend, let's say, polylog time. If you spend the time to do this is something like T, the average update time here, the worst case update time here would be T. just proportion to, like you start with something fast here, you get the same update time here.
So for example, for min-max, the degree could be large, inside S. So do you make some other assumptions about pre-processing or something?
The degree could be large. Yeah, you're right.
I add a new vertex and have a new pass through this vertex for everybody. How can we do it in Polylog? What other assumptions?
Yeah, good question. Yeah, like the way to do it is to make the graph constant degree. There will be some reduction to make that true. But
that comes out kind of outside
of the black box. Yeah. Okay, but at least I hope you see the whole thing, like you saw the whole thing of this one. And this one, you could try to do it yourself. Not complicated. So now let me mention some open problems in this area related to dynamic vertex specifier. So there are a lot, and I think it's quite promising. I'm gonna put a huge table here, and the red highlight below would highlight the aspect that can be improved. And you're not supposed to read the whole thing. You can look up later and see if you want to work on it. And basically, so we saw min-max one. Okay. We saw the offline vertex specifier, the static one. One can make it fully dynamic. That is, it handles both add terminal and as well as delete. So this is one of my previous work. So you could this is kind of solved. But for shortest path, for example, we have this trade-off, which is this is expected to be optimal. However, this trade-off, we have the dynamic vertex specifier only in the incremental case. You can handle only add terminal, so you get only incremental algorithm from it. If this is fully dynamic, if you can handle deletion too, you would immediately get fully dynamic descent oracle, which is very nice. And many other things here. So you can look up in the video and see if you want to work on it. I think it's a nice area. It's a nice question by itself, and it has a good application.
These are all undirected graphs, just to confirm?
These are all undirected graphs, yes.
When you say good application, meaning you get these dynamic outcomes?
Yes.
Okay.
Right, yes. Just inside this thing, inside dynamic area. Okay. So what you have seen so far, right, is a 3 templates of dynamic data structure. Along the way, we set up, you now know a basic terminology in the area. The first template is something like this, rebuild in the background. The second one is how to get from one batch algorithm to dynamic algorithm. That one batch algorithm usually is easier to design. Once you just apply it to rebuild in the background technique, you get dynamic algorithms. And note that it works for a K-batch algorithm too. And this K-batch thing have been used and applied to get more dynamic algorithm in the literature. Last thing is vertex specifier idea. There are more templates that I will not have time to talk about. The recent and quite promising template is the thing that Aaron mentioned in the introduction of this workshop, actually, which is to get to start with some optimization method that is suitable for dynamic algorithm. For example, he mentioned that something like regularized solution. There are ways to compute static solution. It's not dynamic. It's just a static solution that itself is kind of robust enough against update. You should think if you compute flow, it kind of balance your flow such that each edge deletion will not delete a lot of your flow, something like that. Just compute static solution that is good enough, that is robust against update. And you can show that just by rebuilding the static solution that is robust enough against update. You don't need to rebuild too often, something like that. So much more thing to explore here, and I think it's exciting. Or there are ways to dynamize the optimization method itself, to make multiplicative weight update dynamic. There are works on this thing quite recently. And also, even interior point method, one can dynamize that thing by itself and get new dynamic algorithm. For example, they get dynamic algorithm for exact MAC flow in the incremental case. And there are more templates in the literature that maybe not I don't have time to go through. There are given incremental algorithm, you can get fully dynamic offline. But this is this template gives you only offline only. So there are some specific template, a template that is quite specific to some problem. If you have decremental algorithm, you can get fully dynamic algorithm. And there are some work in the past, in the 80s, showing that for many geometric problem that are composable in some sense, if the problem is composable, there is the automatically is a fully dynamic algorithm, something like this. And okay, let's see, 1 second. I want to tell you quickly about what I'm gonna talk about next time. Okay. So the first thing is just a pointer to what I will not cover. Okay. So there recently there is quite nice technique based on expanders that can be applied to many dynamic problems like dynamic connectivity, shortest path in both undirected and directed graph. And this is based on expanded partitioning or expanded pruning. And I have given a tutorial about this thing, and you can look up, and there is the whole course related to this too, if you want to learn a lot about this. There is one technique that I want to mention because it's a technique for matching problem. It works for dynamic matching, but what is so interesting about this technique is called edge degree constraint subgraph. What is so interesting about this technique is that it's a technique that applies in so many area, not just dynamic, but streaming, sublinear algorithm, and communication, and so on. So they're kind of a model independent techniques. So if you want to work on matching, this is something to look at. And Aaron gave a tutorial on this, and I put the link, and I will upload the slides. Yeah.
A different Aaron.
Yeah, Aaron yes, thanks. Aaron Bernstein. Okay. Another one is called randomized greedy. This is like a general approach that works very well for symmetry breaking problem like maximal matching, maximal independent set. It's like a one techniques that likely will work to more problems, and you can have a look at Sohail's tutorial. What I will talk about next in the next talk is to focus on adversaries. So when you use dynamic algorithm and interact with optimization method, now you need to care whether like this interaction is adaptive or not. And so in next talk, you will learn a different kind of adversaries. There are many kinds actually. And you will see templates again, like template of designing algorithm for different kind of adversary. Right. And I think that would conclude for today. Thanks.
Thank you. Questions?
Hello. So I just had a question on template 3, like the Vertex specifier. I wanted to ask, is like the method of like splitting between like permanent, non-permanent edges, does that also work for different composable structures, for example, like edge specifiers? Like, can you also do that to create dynamic algorithms?
So the question is like this composable vertex specifier. If you have a specifier that is composable, would it give you some dynamic algorithm? Yes, usually like there is like a work called specification by Epstein et al. Like in the 90s, like 97, which really like use this idea. However, the speed up that you will get is gonna be like, it's gonna look like this. If you have algorithm that have running time depends on M, you can replace it with running time that depends on N. So just like kind of more modest speed up.
Okay, thank you.
More questions? Okay, let's thank Thatchaphol again. So we're not done for the day.